Well, this section is probably one of the most interesting components of the ASK transmitter. The goal for our transmit filter is to take the result of the binary message which passes through the signal point mapper, and that simply converts the binary symbol 0 to traditionally 0 volts, and the binary symbol 1 to some non-zero value, in this case square root of the energy per bit. So we have these two, what we might think of as analog amplitudes, which then get applied to the transmit filter, and the transmit filter works from some prototype pulse shape. It then applies the amplitude that's being specified by the signal point mapper and uses that to generate the analog pulse that ultimately gets sent through our channel. Now, to have something tangible and fairly easy to work with, I'm going to use a decaying exponential for this running example. This has the form of e to the minus t over t sub b, and you're hopefully familiar with this from looking at first order circuits, transient responses like RC circuits and so on. But let's have this extend over our bit interval t sub b, and it's 0 outside that interval. So only non-zero values within the range 0 to t sub b. And 0 otherwise. This is not necessarily a good pulse shape to use for communication systems, but it does give us something easy to talk about right now. So we can think about this as being an analog signal, but in a digital type system we need to discretize this at our sampling frequency of f sub s. So I'm looking at this exponential shape, and I can vary my sampling frequency in a fairly continuous fashion, and I'm also displaying the reciprocal of frequency, which we call the delta time, or you could also think of that as the sampling interval. Now here we can see that the actual data points become much more clear as we're at lower frequencies. And I'll switch to this line style plot, or what you might call a stem type plot. Again, that spacing, called delta t, would show up back here. So if we start at time 0 and move forward by this delta t amount, move forward a little bit more, so now we're at twice delta t and so on. Again, delta t is our sampling interval. Then we think of the sample points as being the pulse shape evaluated at those integer multiples of delta t. And one of those sample points is back at 0. Altogether, we have t sub b, which has units of seconds, times the sampling frequency, which has units of samples per second. So altogether, that product gives us the total number of samples for our discrete time pulse shape. Now I'm going to define our pulse samples as this sequence p sub k. So our very first sample would be p of t evaluated at t equals 0. So that's pretty easy, p of 0. The next one would be p of t evaluated at t equals 1 delta t, or p of delta t, and so on. So we keep evaluating it at integer multiples of delta t until our very last sample then would be t sub b times fs, our sampling frequency. And I'll omit 1 from that to account for the fact that we already had p of 0 at the beginning of the sequence. That also allows us to dovetail the pulse shape into the next bit interval. Now I'm going to switch gears here for just a moment and draw your attention to the FIR filter equation. And at some point you've probably studied the finite impulse response filter, which operates from a sequence of filter coefficients, b sub k. These filter coefficients multiply your input sequence x to produce your output sequence y. Now if we let the input x be a delta function, then y becomes the special function called the impulse response. Impulse response is denoted as h of n. So it's the same expression, except now I've simply swapped out x for delta. The delta function is a 1 only when our index k is equal to n, otherwise it's 0. So as we start to evaluate this sum, we see that we have b sub 0 coefficient times delta of n minus 0 plus the b1 coefficient times delta of n minus 1, and so on, all the way out to k equals m. So those set of shifted delta functions means that h sub k now is also a sequence, and it's simply b sub 0, b sub 1, b sub 2, and so forth, all the way up to b sub m. And that sequence is the same thing as the filter coefficients. All right. Now, here's the cool part. We see a nice relationship between the impulse response sequence and that pulse shape sequence that we were discussing earlier. So we're going to use the pulse shape samples as the FIR filter coefficients. Now this is got some other stuff going on here, but the thing I want to draw your attention to is this FIR filter that you'll be using for the transmit filter. Here we apply the input stream, here we apply the FIR coefficients, and our filtered result pops out the other side. Now this chunk right here is where I'm generating the filter coefficients corresponding to that exponential shape. So we'll keep using that running example. The impulse pattern generates a single impulse at time 0, or you can delay or shift that impulse as needed. So what I'm looking at here is the exponential pulse shape. We can see that we were looking at earlier. I've got this thing scaled so that we can also see negative versions of this eventually. You'll also notice that the FIR input is a single impulse at time 0. So that impulse generates a whole series of output pulses. If we increase the sampling frequency, we decrease the sampling interval, and so we can make that as dense or as sparse as we like. Now as I start to increase the total number of bit intervals that we're talking about here to 4, for example, what I'd like to be able to do is actually get a delay so that it's possible for the input impulse to cause this exponential pulse shape to get generated in a different bit interval. So if we delay the input, we expect to see that the output is likewise delayed. So that way we now have a mechanism for controlling in which bit interval that pulse gets generated. So we do that by deciding at which bit interval we actually pop the filter with that impulse. Now what we'd really like is the ability to manipulate the amplitude of the prototype pulse. So we're going to do that by manipulating the amplitude of the impulse that drives the filter. Now in order to see something happen here, since I've not actually got the amplitude wired into my event structure there, I have to adjust another control to make the application wake up and respond to the front panel. We have this general idea now that we have this prototype pulse. We can place where we want it to occur, and we can also adjust its amplitude based on how we set up the amplitude of that input impulse. All right, finally, it would be nice if we could generate a whole bunch of impulses, not just one. And we've got a nice device here. It's taking me just a moment to see it. Let's try that again. There we go. It's called upsample. See what upsample has to say about itself. It says insert 0 in the input sequence X by some upsampling factor. All right, let me go ahead and just take a quick time out and rearrange the block diagram here a bit. I've now got upsample inserted. The total number of samples for a given bit interval is used as our upsampling factor, and then now I have an array style control in which I can apply a whole series of different pulses to the filter. Now at the moment the array only has one value. Let's add another one. Okay, now we can see that our second pulse is getting generated here with a negative amplitude. Let's see if we can make a third. And a fourth, and so on. So this is really the main idea, is that we generate a series of spaced impulses and apply those to the filter, and that generates the so-called analog waveform that we need. Now, just to kind of emphasize that notion of an analog type waveform, let's increase the sampling frequency dramatically. I'll change my plot style. And so that, for all intents and purposes, looks like a nice analog type waveform that we're generating. All right, let me revert back to just a single impulse at the beginning, but I want to keep the number of bit intervals spread out to 4. Now supposing I do a little bit of a manipulation here such that the exponential exists over multiple bit periods. In this case, the exponential exists over 2 bit periods. And this actually happens all the time with communication systems, where you might have your prototype pulse extending over many bit periods, as it turns out. So here's the beauty of using this FIR filter approach. What I'm doing now is hitting it with 2 distinct impulses. So we generate the beginning of our first pulse, and then we add in or superimpose the pulse for the second bit interval, but we do that even while we're still working on the pulse from the previous interval. So the filter automatically handles that superposition that we need. So this works really well for us, and you can use really an arbitrary pulse shape once you've got this basic pattern set up. So the signal point mapper will take care of generating the appropriate amplitudes on the upsample device, and then the FIR filter will apply whatever your desired pulse shape is to generate the signal before it gets to the multiplier for modulation.